So in the last lecture, we had stopped at the derivation of the bilinear form for the finite element solution, and we had talked about the orthogonality of the error. That is, what is the orthogonality condition? So let me reiterate what the orthogonality condition was. We got d u minus ufe comma v is equal to 0 for all v's given by this representation. That is, all v's which could be represented as a linear combination of our global basis functions that we have used for the approximation, and such that v also satisfies a geometric constraint, that is a geometric condition at, for example, for the problem we have at x equal to 0, u is equal to 0, so v at 0 has to be also 0. For all such v's, this is true. So we had said that one candidate v is ufe itself, because ufe satisfies the 0 condition at the point x equal to 0 for our problem, and it can also be represented in terms of the shape function, the basis functions, as we have done. So from this condition, we reached the conclusion that d u comma ufe is equal to b of ufe comma ufe. So now we are going to use it for determining what is b of u minus ufe comma u minus ufe is equal to. First of all, physically, what is this equal to? So let us go back to our definition of b. So b of, if I put some function u comma u is equal to integral over x is equal to 0 to L Ea du dx whole squared dx. Now what is this quantity equal to? This is, as we had done earlier, it's twice the strain energy due to the function u. So if I have a deflection u, due to the deflection u or displacement u, we have a strain in the material. The strain leads to a stress, and the strain energy of the body is equal to my calligraphic u. And it turns out that b by this definition is nothing but twice the strain energy of u. So when I am talking of the b of u minus ufe, first of all, u minus ufe as we had defined is equal to the error in the solution. This is the exact, this is the finite element, the difference of the two is the error. So this is the error. So I could write b u minus ufe in the short form. This is equal to b e comma e, which is nothing but, by our definition, twice the strain energy of the error. What does this mean? That if I give a deflection or displacement which is equal to u minus ufe to my body or this bar, then the strain energy due to that displacement is going to be u of e. Fine. So if I have the strain energy, then I can expand it. I know that this will be equal to bu comma u This is a very simple job to do because these are nothing but integrals. We expand the integrals out and you can see the bilinear form coming out to be of this type, minus twice b u UFE plus b of UFE comma UFE. Now, this quantity that we have here is already known. How is it known? Because we have written this quantity in terms of its equivalent definition as b UFE comma UFE, twice of that. So BE comma E becomes minus B UFE comma UFE. So what does it tell me? If I look at BE comma E, by the definition of the integral that we have given here, any expression, if instead of U I had put E, then this integral, the quantity under the integral sign, is always greater than equal to 0. Why is it so? Because the integrand, if you see, is a square term. If it is a square term, that is the area under this curve is always a positive area, so this has to be greater than equal to 0. It is true for the U. If I put E, the same thing should happen. So what I know is that here, in our expression here, this quantity is greater than equal to 0. Always. It is equal to 0 when E is equal to 0. Okay, so what do I have then? Because of this, I will have BU comma U minus B UFE comma UFE is greater than equal to 0. But what is this expression equal to? This is equal to twice of the strain energy due to U minus strain energy due to the UFE is greater than equal to 0. Okay? So which means that the strain energy due to the exact solution is greater than equal to the strain energy due to the finite element solution. How does it translate into the parlance that is used in the finite elements literature? This means that since the strain energy due to the exact solution is greater than that of the finite element solution, we say that the finite element solution is stiffer than U. Okay. One thing we should keep in mind that all this could be done provided the UFE satisfies the homogeneous boundary condition. That is, this is only true for problems where the geometric constraints are homogeneous in nature. If they are not, you cannot say anything about that problem. Okay. So we know that the finite element solution is stiffer. In what sense? That is, the strain energy due to the finite element solution is always lesser than that of the exact solution. So this could be a very good check for the finite element program that one writes. That if I have a problem with geometric constraints which are homogeneous in nature, then, and see, this is true irrespective of what my bilinear form is. This is a generic representation. So what if I have that problem, I solve, then I should see that as the solution is refined, that is, I take more elements in the mesh, that is the n is increased, n is the number of elements, increase n, or I change the p. P is increased. In both cases, I would expect that the strain energy due to the finite element solution should approach the strain energy due to the exact solution from below. Okay, and it should be a monotonic convergence to the strain energy of the exact solution. If my strain energy, the computed strain energy, goes like this, that is, it is sometimes increasing, sometimes decreasing, then something is wrong with my finite element program or the computation that I have done. Obviously, one question that will come to mind is, how do I compute the strain energy of the finite element solution? So if I look at the strain energy for this simple problem, it is equal to half integral of x is equal to 0 to L. I am writing it in a loose way because we should have taken summation over the elements. It should be EA DUFE dx whole square dx. Now, what is UFE equal to? UFE is equal to sigma of UI phi I. So this will be equal to, I can rewrite it, is integral x is equal to 0 to L EA into sigma I is equal to 1 to NP plus 1. P is the order of approximation, N is the number of elements, so total number of unknowns is NP plus 1 into UI d phi I dx whole square dx. So what will this be equal to? This will be equal to, if I expand it out, it will be summation I is equal to 1 to NP plus 1, summation j is equal to 1 to NP plus 1, UI uj integral x is equal to 0 to L EA phi I prime phi j prime. But what is this quantity? This is nothing but our global stiffness entry Kij. So this summation will be equal to half of U transpose into K into U. So when I have solved my problem, I obtain this vector U. So I already have my stiffness matrix, the global stiffness matrix. So all I have to do is take this product. This is the strain energy of the finite element solution. So this is very easy to compute. And it is certainly, for when one is writing a code, it is healthy practice to do these checks. Create problems for which I know what the finite element solution should do, and then check whether my code is really doing that or not. Okay, so we have said that the finite element solution is stiffer. Now then the question is that this is equal to U of the error. What does this signify? If you see that when the finite element solution is equal to or is the same as the exact solution, the displacement due to the difference of these two solutions, that is U minus UFE, becomes smaller and smaller. That is, as UFE goes closer to U minus UFE becomes smaller and smaller. Because of that, the strain due to the error, which is U minus UFE, becomes smaller and smaller. When the strain becomes smaller, the stress becomes smaller, so this also becomes smaller. So as my finite element solution converges to the exact solution, the strain energy due to the error should fall down. Question is, at what rate? So UE comes down at what rate? To see that, let us take a simple problem. Again, I take a loading F is equal to x squared. Here I put P is equal to 1 and I put the material EA is equal to 1 and there is no distributed spring. Length is 1, this is x equal to 0, this is x equal to 1. So the length of the bar is 1. I've taken the loading as x squared. So obviously I know that this problem becomes, the differential equation is given by this. And u0 is 0 and du dx at x equal to 1 is equal to 1. For this problem, since this is the second derivative of u equal to x squared, the exact solution is fourth order. So u exact will be equal to minus x to the power 4 by 12 plus ax plus b, where the a and the b are easily obtained from the boundary conditions. So this is going to be my exact solution. Now for this, I would like to take a mesh with uniform elements, that is all elements have the same size h. The mesh size is h, and so the number of elements n is equal to 1 by h. What I will do is, I will use an order of approximation over the full mesh of either order 1 or 2 or 3. So what I am going to do is fix P, that is fix P, and then refine the mesh. That is, I am going to take n is equal to 2, 4, 8, 16, 32, 64 and so on. So for these various meshes, that is, I have taken P equal to either 1 or 2 or 3, and for this P, I take the number of elements in the mesh as 2, 4, 6, 8, 2, 4, 8, 16, 32, 64. So it's doubling every time. Now for these meshes, I go and find the finite element solution. So what do I expect? As the mesh is becoming finer and finer, the error, that is the U minus UFE, should become smaller and smaller. That is, UFE should approach U. So we expect as we do this, E should decrease. Now we would like to know how fast does the E decrease with respect to the H, that is the mesh size, and the fixed order of approximation P. So I have the fixed order of approximation P and H. With respect to these, how fast does it decrease? So what do? We don't look at the error directly, we look at the strain energy of the error. Now let us look at the figure plot of the decay of this error, because we know here what is the exact solution. So error we can find. The decay of the error as the H is reduced, that is the number of elements in the mesh is increased. So for the fixed P, we will do this. and what we are going to plot is log of square root of the strain energy of the error versus log of h. These quantities we are going to spread to plot. So let us look at the plot. From the plot you see that the first line, which is the blue line corresponds to the p equal to 1 approximation, and you see that the error decays. This log of the square root of the strain energy of the error decays with a slope of 1. So slope is approximately 1. It's 0.9743, but it's approximately 1. Now if I go and fix p equal to 2, then when I plot this, the slope of the line is approximately 1.98, which is 2. For p equal to 3, you see that the decay in the error, the strain energy of error, is approximately 3. So can I reach a general conclusion out of this? The answer is yes. Though this is only a particular example we have taken, it demonstrates the nature of decay of the error. And it turns out that square root of strain energy of the error is less than equal to some constant c into h to the power of p. Look at this carefully. What should this c depend on? Don't bother about it now. What it says is that if I fix the p and I change the h, that is, I refine the mesh, then the strain energy of the error decays or falls down at this rate. Okay? Why strain energy a measure that we are using? Because strain energy is never negative. Okay? So when the strain energy becomes 0, we know that our exact solution and the finite element solution are the same. Okay? So this is called the a priori error estimate for H version of FEM. What do we mean by the H version? There are two or three various approaches we can take to reduce the error. So our job is to get the finite element solution as close as possible to the exact solution. We can achieve that goal through different approaches. So one approach that we have taken is we have fixed P, we have only refined the mesh, so this is called the H version. That is, only H is changed, the parameter H. Another approach that you can have is we fix the H, fix the mesh, and increase the P. If we increase the P, then we get the E version of the finite element method. So we are not refining the mesh, we are only increasing the P. With that we get also we hope that the error comes down, and indeed for such smooth problems this can be exponential rate. So the decay in the error is exponential. So now the question is, when this is exponential, why don't we use this? The answer is that this depends on the smoothness of the solution. The C plays a role. How good is the exact solution itself? And in problems where we have domains with corners, etc., where the solution is not smooth, in that case the P method will not do as good a job as we have shown here. Similarly, the H method will not do as good a job as we have shown there. So in that case you have to have an interplay between the H and the P. So that gives rise to the HP method. So in the HP method, what is done? Both the H and the P are suitably changed in order to get good convergence of the solution. Okay. So this is about the convergence of the error in the strain energy, or how does the strain energy of the error converge. Now obviously there are other questions that come to mind. is how do the pointwise values of the error behave. So if I have t equal to 1, let us look at the next figure. From the next figure we see that the error at the nodes, the corner nodes, is 0. And because it is the same problem that we had taken with the exact solution of the type x to the power 4, so we find that the error at the nodes in the value is 0. For this problem, we get that the nodal values are exact. Now something more curious. We are, as we had said, we are interested in the derivative information much more than the value of the displacement itself. And if you look at the second part of the figure, in the second part of the figure you will note that the derivative of the error vanishes at the midpoint of the element. So midpoint of the element derivative of error is 0. So the derivative of the finite element solution is very good at the midpoint of the element. What else can you note? You see that at the end of the elements, at the end points of the element, the derivative of the finite element solution is very far from the exact one. If you look at the error plot, this error is quite high at the nodes of the elements. This is a very important feature of the finite element solution. In fact, this is a drawback of it. Though we know that in the physical situation, in the continuum, the derivative of the solution has to be continuous unless we have a material interface. Here we have no material interface, it is only two elements. So at the interface of the elements we should have had continuity of the derivative, but it is not. In fact, that is very bad. And you see that from the two sides the value need not be the same. The value of the difference, that is the error of the derivative, need not be the same. This is also called the shattering phenomenon. Okay. So let us now go and see whether the situation improves when I take t equal to 2. That is the next figure. Okay, so if I look at t equal to 2, then we observe that the nodal values are exact, and at some point in the middle, most probably at the center of the element, which is also for the Lagrangian element a node, a solution node. At these 3 points we find that the solution is very good. Okay, but really speaking, we can only say in the general case, though for this one we observe these things, that the nodal values are exact. Okay. It turns out that here also the midpoint is good, so be it, but we cannot generally make that statement. What about the derivatives? Now you see that curiously there are 2 points in the element where the derivative is very good. So du fe dx is good or exact in this case at 2 points in the element. Obviously, it is quite clear from the figure that this is a 3-element mesh. So we have 3 elements of the same size, okay, for which we find that in each of the elements the derivative of the error vanishes at 2 points. Okay, when t is equal to 2. This is a very curious thing which is a feature of the finite element solution. And so when I have t equal to 2, I have 2 points where the derivative of the error is 0. Okay. So let us now go to the next figure, which is the t equal to 3 figure. Here you look at the behavior of the error. The error has a kink at these endpoints. of the element, and the derivative again jumps a lot. That is, the error at the endpoints of the elements in the derivative is quite high. While now, if you see within the element, there are 3 points. So as far as nodal values are concerned, nodal values are exact. Okay, nodal values are exact, but there are 3 points in the element where DUFE is very good. At 3 points in the element. In each of the elements. You see that there is a trend. If you see the trend, then generally for a p-th order element, we should get p points of good DUFE dx. These points in the general case are called points of superconvergence. So remember that instead of getting answers, we have created more questions, in the sense that what do we do at the inter-element interface? That is, if I want to get the derivative of the finite element solution accurately at this interface of the two elements, at the corner nodes, what do I do? So that is something that we are not going to discuss now. Good values of the derivative, they can be obtained by a suitable averaging. Now obviously a very simple thing that one can do, if I look at the linear case, one averaging that we can certainly do is, if I have these three elements, we find that at the midpoint of the element the derivative is very good, so we can pass a straight line between the values of the finite elements, the derivative of the finite element solution. Okay, so that straight line, so this is UFE prime at this point, UFE prime at this point. Then maybe the value here is this, and between these two I can pass a straight line. So I can do various kind of fitting to get a supposedly better value of the derivative. That is by itself a whole field, and we are not going to indulge in that now. Okay, so we have seen that how the solution converges in the global measure, which we have defined as the strain energy, and as well as in the pointwise sense. Now what we should be careful about is, this is very, very specific, especially the pointwise result, to problems with EA equal to constant and K equal to 0. If EA is not equal to constant, if I have this kind of a situation, this part, or in case I have a bar with axial springs, distributed axial springs, in both cases you can see that the nodal values is not exact at the, so UFE is not exact at the nodes, that is, the nodal values are not exact. However, these nodal values are very good. Not exact, but they are very good. Similarly, the derivative will not be the way it has shown here. It will be very good at these points that we have shown with our example. Okay, so now we have talked about the error for such problems and how it converges. So one can go ahead and write a finite element program and use it to solve the problems, and based on the kind of accuracy you want and the kind of computing power one has. So again, remember that the things that we have to look at are accuracy and economy. Computational cost is very important. Why economy? Because here if we have a pth order element, then we will have np plus 1 unknowns. Okay. Here the rate of convergence in the strain energy is of the type ch to the power of p. So we will have to have the interplay between these two things, because if this is so, then the number of computations or number of floating point operations that have to be done in order to find the inverse of the K matrix, which is also of this size, is np plus 1 cubed. So the cost will be given in terms of the number of operations will be of the type np plus 1 cubed if I use a standard Gauss solver. Okay. So we have to look at the cost of the computation as compared to the accuracy we want, and accordingly we will have to decide on which approach to use. That is, whether I should use higher P or smaller h or whatever, or a combination of these two things. But for the example problem we have taken here, obviously taking higher P is more economical. That is, fix a mesh, take a 2-element mesh and increase the P. Then the cost of the computation will be smaller. Okay. So once we have determined these things, so let us now again reiterate or go over what are the various pieces in a standard finite element program. So what we have done is, if you remember, that we first started off by making the nodes, and I deliberately first made the nodes, the end nodes of the elements. So if I have to make the nodes, how will I make the nodes? So first I am going to choose my P. So first you choose the P. Based on the P, now you know P and the N, which is the number of elements. So given N, you know H is equal to L by N if I am using a uniform mesh. So let us take a uniform mesh. H is equal to L by N. Now given the P, I have to put these P minus 1 equally spaced points in each element. So how do I find those points? So I will call something as the H bar is equal to H by P. So this is the spacing between two consecutive solution nodes. Okay. So how do we now go ahead and make the mesh? So I have to make the mesh. So solution nodes, so I start with x1 is equal to 0 or the given value, and then we say x1 plus I is equal to x1 plus I h bar. This will give me the mesh. So once I have the mesh, then what do? Then we have to construct the shape functions of the so the mesh generally falls pre-processor. What other information we should create here? So after making the mesh, we should also give the element information, that is, in the element K, which are the nodes? These nodes that we have created, these points. They are important because we would like to know the extremities of the element, as well as we need these points to construct the shape functions. So if I have this thing, then I know that it will start with plus 1 to p into k minus 1 plus p plus 1. Okay. So these are the nodes in the element. So this is the set of nodes which are sitting there in the element. However, we know that the first and the p plus 1 nodes are the extremities of the element. Why do you need the extremities? That is, you need x p k minus 1 plus 1 and x p k minus 1 plus p plus 1. So given these two nodes, we can do the integration. Okay. All the nodes are now used to define the shape function. How did we define the shape function? By taking the product rule. You can use available symbolic computation softwares like Mathematica, Maple or MATLAB to get the derivatives of these expressions, that is the shape functions, because for the linear quadratic it's easy to do. For the higher order elements it may be a little bit cumbersome, so it's better to let the software do it. We could do it by hand also, but it will take time. So once I have this information, you see that the other thing which is there, I really need these numbers. Once I have these numbers, it is also the local to global numbering that we were talking about from the assembly point of view. So this number gives us all that information, that from the assembly point of view, where does the local entry go to globally, as well as what is the coordinate of the point corresponding to this location. That's why generally in the 1D approximation where we use this kind of a Lagrangian shape functions, these nodes, which were the solution points, they are indistinguishable from the geometric points. So they are both called nodes. But the solution value is called the degree of freedom. So at every node there is a corresponding degree of freedom, which is the value. So this is the problem has np plus 1 degrees of freedom or unknowns. Okay. So once I have the mesh information available, now for the element I have all the relevant information, then I will do the element calculation, which we have done in some detail, which will give us the element stiffness matrix and the element load vector. Then we will do the assembly process. Then we apply the boundary conditions and then solve. Solve means use Gauss elimination or any solver which you must have already studied. This whole part is called the processor. In a finite element code, this is called a processor. Now after we obtain the solution, as we have seen that the direct finite element data, especially the derivative information, may not be so good. Even if it is acceptable to us, then we will have to display them. So display becomes a very important point, or we have to output the values of these of the finite element solution as well as its derivatives at some points. So output response info. Okay. So here we may do direct information is outputted or some processed information. This whole part of outputting in the form in which I want it, this is taken care of in what is called the post processor. So So a finite element program will have these three big components, and in the three big components we'll have several smaller jobs. So now you can see very clearly that it is already broken into modular form, and the modules can be separately programmed, integrated and used. However, here there are certain problems that we have to face. Till now we have dealt with very simple problems where the EA was constant, F was relatively simple, and still when you go to higher P's, this whole business of integration becomes very cumbersome. When the material is varying, that cross section may be varying, or the material is varying, or in case the load is not a typical load, it is a given realistic load. In all these cases, doing this job in a closed form way, all the computations we have done till now were closed form. In a closed form way may not be so easy. So what we would like to do is to let the computer do the integrations for us, for which many of you must be aware of it. We use numerical integration. So we would like to use numerical integration, that is, instead of writing the integrals, we would like to use summations. Now to do that, we'll have to change the way we have done things a little bit. The whole process remains the same, but now we are making it more amenable to a computer implementation. Till now, most of the things were done by a hand or by a symbolic computing platform. Okay. Here we would like to write a program which can do these numerical calculations, give us the stiffness matrix and the load vector entries, and go ahead and do the assembly and everything else. So what we will see in the next set of lectures is how to do this job of transferring what we have done till now to a computer. Okay? So we will introduce the concept of master element, how we define everything with respect to the master element, how do we transform our physical domain to the master element, and do the integrations, convert it to numerical integration, and so on. Thank you.